Just a reminder that we will be recording today. So for those online, if you don't want your video to appear, now would be the time to turn it off. So first up today, we'll actually be hearing from one of our co-organizers, Xiurui Zhao. Xiurui is a second-year postdoc here at the CFA. He got his PhD at Clemson University in 2021. He was also a pre-doc here at the CFA from 2020 to 2021. Xiurui's research focuses on AGN and X-ray, and he now also is interested in multi-wavelength study of AGN. So today he'll be talking to us about active galactic nuclei in the NuSTAR era. So Xiurui, go ahead.
Thank you, Amy. Thank you, everyone. So one good thing, I think, being an organizer of the seminar is that if there is a spot available in the next week, you will have the chance to present your work voluntarily. Thank you very much. Today I'm going to talk about the active galactic nuclei in the NuSTAR era, and I know that many of you are experts of Quasar, AGN, and also NuSTAR, but please bear with me for the next few slides of introduction. So active galactic nuclei or AGN it represents the rapidly growing phase of the supermassive black hole in the center of the active galaxies. So it radiates across the whole entire electromagnetic spectrum from radio to gamma rays. So in the different energy band, it can tell us the different aspects of the AGN. For example, in the radio band, it can tell us about the jet of the AGN. And in the infrared band, it can tell us the AGN torus. In the optical, it tells us about the accretion disk. And also the broad emission line in the optical band can tell us, for example, the supermassive black hole mass. And also in the X-ray, it can tell us about the hot corona, which is the X-ray emitter in the AGN. So the corona is a bunch of hot electrons that it will upscatter the UV and the optical photons created or produced by the accretion process up to the X-ray band. And this process is through the inverse Compton scattering, so that you can see the X-ray spectrum or the X-ray photons from the AGN. And the X-ray band can also tell us about the properties of the dusty torus. So the dusty torus can reflect the intrinsic corona emission into the X-ray band, and it will have a different spectral shape if you have a different properties of AGN. For example, if you have a different density of different density of the torus or different size of the torus, then you will have a different shape of the reflection component. So the X-ray band can tell us both the corona property and also the torus. And the gamma ray band can tell us also the AGN jet. So today my talk is focused on the X-ray part of the AGN. So why do we study AGN in X-ray, or why X-ray is unique in studying AGN? So firstly, X-ray, especially in the hard X-ray band above 2 keV, they are less diluted by their host galaxy emission. So in this figure, I show an image of a nearby AGN NGC 3783, which in both optical band and also in X-ray. And in the left panel, you can see clearly that in the optical, you see both the emission from the host galaxy, like those spirals and the bulge. But in X-ray, you only see the AGN emission, the central nucleus emission. So this suggests that if you observe AGN in X-ray, you can get the pure or almost the pure emission from the central AGN without too much dilution from the host galaxy. And also the X-ray will select the much pure AGN samples or populations than the other wavelengths, especially than the optical. For example, let's go back to the ICD, this figure. In this figure, the author also plots the starburst galaxies ICD in the gray line. And you can clearly see that it's difficult for the starburst or star-forming galaxy to produce the X-ray emissions, or their X-ray emissions doesn't dominate their ICD. So the X-ray band can select much pure AGN in these perspectives. And the X-rays are also less affected by the obscuration, which I will introduce in detail in the later slides. So after introducing the AGN, and it's interesting to study AGN in X-ray, so what is NuSTAR? So NuSTAR is the first NASA telescope that focuses hard X-ray, especially above 10 keV. So unlike Chandra and X-band, which focus on the soft X-ray from 0.1 to 10 keV, NuSTAR has an energy coverage from 3 to 79 keV here. And it was launched in 2012. The PI is Fiona Harrison, and it was operated in the low Earth orbit. And it's one of the smallest X-ray telescope, I mean, in terms of the budget. But it has very long focal length, about 10 meters. That's also similar to what Chandra has. And this long focal length can help NuSTAR to have a comparable angular resolution of like in the soft X-ray telescope. I mean, it's not definitely Chandra resolution below. I mean, it's not a sub-arc-second resolution, but still below arc-minute. So the long focal length is very important for the hard X-ray telescope. And to save the budget for launching, the NuSTAR engineer found a very innovative way to shrink the size of the telescope before launching. That the whole telescope was connected. I mean, the optics and the detectors was connected by the mast, a 10 meters mast, and that 10 meters mast was folded before launching, so make the size very small. But then when it was launched in the space, it was deployed to the 10 meters long. And I will show in this cartoon that animation, that before launching, NuSTAR was like this, and that is the optics, and this is the detector. And when it was launched in the space, you can see the mast was deployed in the space to that long, 10 meters long. And to actually measure, I mean, to calibrate well the precision of the optics and also the detectors, there is a whole laser system to help this calibration. So you get a very aligned optics and the detectors. And also this can help us to save the budget. And this technique is also used in the last year launched the XP telescope, a new X-ray probe telescope. So in this slide, I'm going to show you the capability of NuSTAR. So as I mentioned, that NuSTAR is so far the NASA's only telescope that focusing hard X-rays. And in this figure, I show the effective area of different soft X-ray telescope compared with NuSTAR. And you can clearly see that NuSTAR has the highest photon collecting area above 6 keV. And this makes it very unique to study the hard X-ray of different types of sources. And also, as I mentioned, that the X-ray is good to study heavily obscured AGN. Here, I show the X-ray spectrum of AGN with different obscuration from unobscured AGN to the heavily obscured AGN. And you can see clearly that for the heavily obscured AGN, their soft X-rays are heavily absorbed, and the majority of the photons from heavily obscured AGN is in this hard X-ray band. And this hard X-ray band is where NuSTAR has the good capability. So NuSTAR is very good to study the heavily obscured AGN. So today I'm going to talk about the three aspects that I was working on in the last few years. And firstly, the AGN density torus and the corona of the AGN, and also the demographic of the AGN. But today, because of the time limits, I'm going to focus on the first topic, which is the AGN density torus. So AGN can be divided into two types or two categories based on their optical spectrum features. So on the left, I show two types of AGN optical spectrum. And one type is type 1 AGN. You can see both the narrow emission line like oxygen 3, or you can, and also you can see the broad emission line like H beta and H alpha line. So this is type 1 AGN, and the type 2 AGN, you can only see the narrow emission line without any the broad emission line. And in 1990s, the people have this AGN unified model, which assume that all AGN actually are intrinsically the same kind of objects, and different types of AGN, type 1, type 2, they are observed from different angles. And the type 2 AGN, where you don't see the broad emission line, are those AGN whose broad emission line region are obscured by the dusty torus. And on the right figure is a sketch of this unified model of AGN that you have in the center the supermassive black hole and the accretion disk here, and outside the accretion disk there are some clouds or clumps of gas that can be ionized and produce the emission lines like the what you see in the optical spectrum. And because they are so close to the supermassive black hole, you can see the lines, some of the lines will be broadened due to the Doppler effect. So you see the broad emission lines. And outside that broad emission line region, where it is cool enough, is far away from the central supermassive black hole, the dust can survive. So you have this dusty torus structure, which provide a lot of obscuration. And outside the torus, there are some also clumps of dusty gas, and because they are far away from the central supermassive black hole, you see only the narrow lines because their Doppler effect is very weak. But they are still broader than the normal galaxy emission lines. And the unified model, like I listed there, it assumes that the type 2 AGN are those AGN your null set, your observing angle are across the torus. So your broad region there are obscured by this torus. So you can only see the narrow lines scattered from the narrow emission line region. But for the type 1 AGN, you can directly see the broad line region and also the scattered emission from the narrow line region. So that's what this model assume. And there are indeed many observations support the model, but we also know that it's not 100% accurate. But what we know is that the torus is a significant component of the AGN. However, torus is still a highly unknown structure so far. For example, is this torus dense and large enough to really obscure this central brown line region? I mean, if it has for example, what are the density or what is the current factor of this torus? The current factor is the fraction of the sky that is covered by this torus. If the current factor is about 0.1, then it's a disk torus. If the torus, if the current factor is 1, then it's a spherical torus. It obscures the whole central region. So we don't really know. I mean, we have some measurement, but it's still a question of what is the density and the size of the torus. And another question we have in recent decades is that we found that the torus is not a smoothly structured that, as I show in that unified model figure, but it's actually non-uniform, it's inhomogeneous. But we don't really know how inhomogeneous is this torus. In the last few years, we are trying to answer these two questions, the density, the current factor, and how homogeneous is this torus. But before I dive into the results, I want to revisit the AGN X-ray spectrum again in details. So the AGN X-ray spectrum are composed of two main components. One is this left-side component, which is plotted in the cyan in this plot. And it's the intrinsic corona emission that is absorbed or obscured by your line of sight dusty gas. So you will see that this is the intrinsic emission with another absorption on that. And another main component is the reflection component. And this reflection component is plotted as a purple in this figure. And this is the intrinsic corona emission reflected or reprocessed by the dusty torus. So you will see you see a very different shape between the reflection component and also the line of sight component. And this reflection component, as it is reflected by the torus, so it contains the information of the torus. For example, what's the current factor and the density. So the reflection component can tell us the torus property, and this is the component we want to get, and we want high signal to noise ratio of this component. However, for the unobscured AGN, as I show in this figure, most of the AGN spectrum, which is the black line, is dominated by this line of sight component. But I will show you that later when it's for the heavily obscured AGN, the AGN spectrum is dominated by the reflection component, and they are the best sample to study the AGN reflecting component and the AGN torus properties. Here I will show animation of varying the line of sight column density of the line of sight component, and I will keep the reflection component the same, that to make things very simple and you can compare easily. So you can see that as the line of sight obscuration or line of sight column density increase, this line of sight component is heavily absorbed and weakened. But in the heavily obscured regime, like here, the purple or the reflection component really dominates the whole X-ray AGN X-ray spectrum. So the heavily obscured AGN is actually the best sample to study the AGN torus. And here I also show the NuSTAR bandpass in the yellow shaded region from 3 to 79 keV, and you can clearly see that the majority of the reflecting component or reflecting emission lie in the NuSTAR coverage, and NuSTAR it will provide significant information of the AGN torus. So to provide an unbiased result of the AGN torus property, we selected 93 heavily obscure AGN using the hard X-ray SwiftBot All-Sky survey catalog. And all these sources, they have high quality NuSTAR observation to make sure that we have the best constraints on the torus properties. In this slide, I will show you what is the density of the torus. So on the left figure, I plot the line of sight obscuration and the average column density of the torus. So remember that the torus is not a uniform structure. It's inhomogeneous. At different line of sight or at different observing angle, you may have different column density. But by averaging this whole different column density, you will have an average torus column density. And this is what the model can tell us. So by compare the line of sight column density and also the torus column density, as in this figure, we can know the different information. I mean, for example, in this figure, the green line, the green dots are the single sources results, and the black dots, they are the average number in different line of sight column density beam. And you can clearly see that the torus column density is on average about 10 to the 24.15, which if we convert it to the optical depth is optically thick if we assume the Thomson scattering cross section. And this suggests that the torus is very thick and it can provide enough obscuration to really obscure the central brown region. So that's why we didn't see the brown emission line in the type 2 AGN. And secondly, we can also extract the property of the AGN torus current factor. And also at different long-side carbon density being, you have very similar torus current factor, which is about 0.67, which is about 2/3. This suggests that the torus is not only thick or dense, it also covers 2/3 of the sky if you sit in the center of the AGN. So it's large enough to cover the center brown line region. And another question is, how inhomogeneous is the torus? We go back to this long-side carbon density and torus carbon density figure, and in the solid line, I plot when these two carbon density are the same, and the dashed line are there are 0.5 dash difference, and you can see that the majority of our sample they have very different carbon density along the long side and their average torus carbon density. And also in this figure, you can see that I plot the torus carbon density divided by the long side carbon density. That is the difference between these two density. And you can see that the majority of the sources, they are not the same. I mean, they do not have the same carbon density, but their torus density is very different from their long side density. And most of the sources have a 3 to 30 times of a difference between these two densities. So very inhomogeneous. And with this 93 sources sample, we know that the torus is dense enough, is optically thick, and is large enough, is covered 2/3 of the central AGN, and also is very homogeneous. And then I'm going to talk a little bit about the AGN corona very quick. And so as I mentioned, that the corona is a large bunch of hot electrons, but the size of the corona is very small. It's below 10 gravitational radius of the supermassive black hole. So it's a very tiny region inside of the AGN. And so it's difficult for us to really resolve this structure, this corona structure. But the X-ray spectra of the corona with different temperature have different shape on their spectrum. And here I show different temperature from low temperature to high temperature corona emission. And you can see the most distinguished region or energy band among different corona temperature are high energy band, which are hard X-ray band above 30 or 40 keV. So that's where the NuSTAR is most capable. And the high redshift quasar, for example, may be the even better sample to study the AGN corona, as thanks to the cosmological redshifting, the AGN spectrum is moved to the low energy band, and you can even distinguish you can have more distinguishable spectral shape among different corona temperature. And this is indeed true that for the low redshift sources, we have mostly lower limit or unconstrained AGN corona temperature, but for almost all the high redshift sources, you have the constrained corona temperature. And last year, we proposed 4 high redshift quasar to observe their hard X-ray spectrum and to get their corona temperature. And the first observation showed that we can indeed constrain their corona temperature, and this high redshift quasar are indeed a good sample. And I will come back to introduce more after all the observations are taken. And so this is my summary that, sorry, I didn't have time to touch the demographic of AGN, but we are doing the NuSTAR survey on the GWT time domain field using NuSTAR, which we get almost already 2 million seconds. and it's now the deepest NuSTAR actual galactic survey. And yeah, and this is the next generation actually telescope we want to advertise. And this is the NuSTAR capability, and this is the proposed HEXP capability. And thank you.
Okay, so let's start with questions.
Really interesting, Martin. Can you explain again how you figure out that a torus is clumpy or inhomogeneous rather than just having an intrinsically high density?
So the question is that how do I find that the torus is clumpy rather than they are intrinsically high density? So I mean, in this figure, this is the line of sight obscuration. So it tells you your line of sight that only in that direction what's the obscuration. But the torus density is the average density of the whole torus. So if you observe the torus in different angle and you average all this density, you got an average density of the torus. And you can see that most of them are not on this 1-to-1 line, but most of them are very different from the 0.5 section.
Yes, so the whole idea of the unified model does go back an extra decade, I would point out. Some other authors, well, I can't remember who they were, who I was, but anyway, why are you biased high in that? Why is it not spread out equally inhomogeneous below and above the mean?
That's a very good question. So remember that we have AGN not only with line of sight complexity of 24, but we also have even obscure AGN with 25, 26. And those AGN, we have only a small sample of them, only 32 of them in the local universe from the sweet spot survey. And those sources, they have very high complexity line of sight, but still the same torus complexity. So if I plot those sources, complexity AGN sources in this figure, you will find that they are like the single sources are like here, the average here. So for those even obscure AGN, their line of sight complexity is larger than the torus complexity. So those sources are populated here. So we actually see a small sample of the whole AGN category, but they actually show very similar or almost the same torus density.
Maybe a naive question, but how do you derive from the data separately the line of sight obscuration and the torus obscuration?
That's a good question. So we have a model by fitting the whole spectrum, and you have different components. And by adding up the different components, you can constrain the different parameters. So, I mean, if you have a model composed of the different components.
Thanks. So this is on a similar line to Lexi's question. If you have a model of the average density of your torus, then you're looking at it with inclination. You would be passing through less of a column density. And so your line of sight column density would be lower. I assume you're accounting for that. I'm just curious how.
Sorry,
Your
please.
integrated line of sight pencil beam, if you're looking at like you scrape the top edge of the torus,
Yeah.
you might only pass through say 10 to the 23
Yeah.
centimeter. But the average density, if you were having to be looking, along, would be 10 to the 24. I assume there's an inclination effect that you're accounting for somewhere.
Yeah.
I'm curious how exactly you're doing it.
Yeah, that's a good question. That inclination angle is a parameter in the reflection component.
Okay.
In the slide number 15, you write unbiased sample. Can you explain what you mean unbiased sample?
So this is a very good question. So even in the SwiftBot hard X-ray survey, it's a hard outsky survey. We find that competent-thick agent or agent with column density above 10 to the 24 that I didn't show here, they are significantly against by their biased against by their heavy obscuration. That is very difficult to discover those extremely obscured agents, even in the outsky survey. That for example, the capability to find all unobscured agent is much larger than the extremely obscured agent, that even they have the same intrinsic luminosity because of the large obscuration, you cannot find them for the extremely heavily obscured agent.
Okay, this 93 heavily obscured again, you check with optical spectrum.
We select from a range of left-side column density so that they are not extremely obscured. We are still able to find them, but we didn't find that biased effect. That, for example, for the competent-thick agent, I mean, those most extremely dense sources, we find as the redshift goes up, you find less and less and less those kind of sources in the sample. But for this kind of sources that we selected, which has a little bit lower left-side column density, but we find that they still their number density are still very consistent at different redshift beams. So
I understand, but my question is about optical spectrum. Really obscured in optical range.
Yeah, they are type 2 AGN.
Only type 2.
They are type 2 AGN.
AGN.
Yeah, they are type 2 AGN with column density between 10 to 23 and 10 to 24.
And a second question about the corona. Your sample include only radio quiet. This picture you show loud, no? AGN.
That's a good question. Yeah, this figure this is one of my collaborators' figure. I need to check with her about if she included the radio loud. But to answer your question, yes, we only include the radio quiet. And this is a very good question because the blazers or radio loud quasars, they may be, I mean, they are actually maybe dominated by the jet. And with the jet, we don't see those corona cut off all the corona features. So that's one thing we did. Yes. Thank you.
Thank you.
Okay, let's thank Xiurui again.
Doing this.
All right, so next up we have Jillian Rastinejad. Sorry, I'm still gonna get that. So Jillian is a PhD student at Northwestern University. She's working with Professor Wenfeng Fang. She conducts optical and near-infrared follow-up of gamma ray bursts to study their afterglow and kilonova counterparts. So Jillian aims to widen the small population of observed kilonova, quantify the diversity of neutron star merger outflows, and make predictions for the electromagnetic counterparts of future gravitational wave events. She also looks for these astronomical transients as a member of the gravitational wave follow-up collaboration Xiurui.
Savara. Yeah, I forgot to give you such a long intro. I'm sorry about that.
And today she'll be talking to us about exciting insights on neutron star merger counterpart.
I changed the title. I'm sorry.
I'll let her tell you this. Take it away.
Okay. Everyone can hear me all right? All right. Well, thank you so much to the organizers for having me and Flor for hosting me. It's my pleasure to be here today. And my new title is about gamma ray bursts as signposts of heavy element formation. So this is a high energy seminar. I'm going to be talking a little bit about gamma ray bursts today, but what I'm mostly going to be talking about is the follow-up that I do of them using optical and near-infrared telescopes. So this is a very famous plot from the BATSI instrument that was the first to really go up into the sky and detect these gamma ray bursts and understanding their.
I'm sorry.
Oh, we gotta share screen or
I try to hide
oh, we can hide. Yeah, we can hide.
this one, right?
No,
Oh.
that's the other one.
Yeah.
And so what Batsy really showed us for the first time is that there are these two populations of gamma ray bursts. So there are these this population called the short gamma ray burst population, and we typically use a duration of about 2 seconds to separate that from the longer duration gamma ray bursts. And so there being these two populations, it was suspected very early on that these gamma ray bursts come from different progenitors. And we didn't know what they were just from their gamma ray bursts alone. And so many other missions were launched, including NASA's Fermi Space Telescope and the Neil Gehrels Swift Observatory. And these are still both flying and detecting gamma ray bursts to this day. So now I'm going to skip ahead a lot of years and a lot of discoveries and work that people have done. And so tying back what we think the progenitors of each of these classes are to what creates them. So we believe that long gamma ray bursts come from the collapse of massive stars. They collapse into a compact object remnant, and from there a jet is launched in this long duration gamma ray burst. We also have a broadband synchrotron afterglow that's detected across the electromagnetic spectrum sometimes, and we can learn a lot about the jet from that. We also, if the event is low enough redshift, detect a core collapse supernova, specifically of the 1C-BL type, so stripped envelope, broad line, very fast moving ejecta supernova. And indeed, we observed this for the first time back in 1998 with the detection of the very famous supernova 1998 BW. You can see it right here in its spiral host galaxy. And so we've detected these for a few years, for several decades now. And we think we have a handle on the progenitor and the event here. But of course, there's so many questions to ask. It took a little bit longer to tie short gamma ray bursts to their progenitors. And indeed, this was only done following the detection of the binary neutron star event, 1708-17, and its detection in gravitational waves as well. Oh, it's funny, you can't see it on the screen. And so with this wonderful event, we detected both the short gamma ray burst and the gravitational wave detected binary neutron star merger. We also detected in detail for the very first time this transient called a kilonova. So these are thermal transients powered by the radioactive decay of heavy R process elements synthesized in that neutron-rich ejecta. And so seemingly every optical telescope in the world turned to look at this event, and we obtained this beautiful light curve set here. And what I want to point out is that we have a very rapid fading in the optical. So this is just the optical G band. You can see it peaks on the order of a few hours and decays very rapidly. This is in comparison to the longer lived near-infrared light curve here, the K band. And so this transition to redder colors at late time is a signature of the lanthanide elements and their filled valence shells of electrons. And that increases the opacity of the ejecta. So we have this one event where we detected a kilonova with it. We detected it in beautiful detail. We were able to obtain spectra of it, mapped it to models, and understand that fraction of lanthanides in it, or at least get some handle on it. And so a question that I think still stands right now is, are neutron star mergers the only site of our process nucleosynthesis in the universe? And so what can we say from observations about their rates and average yields to try to understand this question? So this is, I'm trying to explore that question of what are the sites of our process nucleosynthesis using follow-up to gamma ray bursts. And so I started out my PhD thesis work looking at short gamma ray bursts. And so we know short gamma ray bursts are connected to neutron star mergers. And so how can we use observations following short gamma ray bursts to constrain the diversity of kilonovae? So we can get some rate from understanding how often these happen and their distribution across the universe. And then if we take a look at our observations of them, what can we say about their yields and ejecta masses that they create? Another thing that I've been more recently interested in is actually probing an alternative site for our process nucleosynthesis in the successors to long GRBs. So how can observations following long gamma ray bursts probe an alternate site for our process element production. And this is what I'm going to talk about for the rest of the seminar. So if you're interested in searching for kilinovae, which is something that I am very interested in, one way you can do this is by conducting blind searches and large surveys. There are a number of groups out there that are doing this, like ZTF, and hopefully with the advent of the Rubin Observatory, we'll be able to do this as well. You can also do this by following up gravitational wave events. And of course, we're really excited to do this in the coming months. And this is something that I do with a collaboration that's led by the University of Arizona and Northwestern University and our small but powerful team here, Team Saguaro. We're really looking forward to doing this in May, and we've been spending a lot of time building tools to do this in the last few months. The last way, as I mentioned, is by following up short gamma ray bursts. And this is what I did in my first paper. So I compiled all of the observations in the optical and near infrared of short GRBs going back to the launch of SWIFT in 2004. And so this is a compilation of all those observations, including several that were unpublished from very deep telescopes. And so this plot we called the ratio plot. So on the x-axis is rest frame days post-merger, so rest frame days following the gamma ray burst. On the y-axis, we took the redshift of the GRB and the depth of the observation and took its ratio to the kilonova 17 GFO. So that was that accompanied GW 17817. And so what we've plotted here is GRB upper limits as triangles and afterglow or kilonova detections as circles or stars here. And so what does this show? Well, it shows that kilonova candidates, so these are events where there's been a claimed kilonova counterpart, are more luminous in bluer bands than 17 GFO. We also see that there are deep upper limits of 10 gamma ray bursts, which fall below this 1-to-1 ratio. So if 170817's kilonova were on this plot, it would fall exactly along that 1-to-1 ratio. And so what this is showing us is that for 10 GRBs in the bands that they were observed in, their kilonova was less luminous than 17 GFOs. And then finally, this tells us that rest frame optical kilonova observations show a span of about 100 in luminosity. The other thing that we did with this catalog of observations was we actually tried to connect it back to the ejecta masses and velocities of the kilonova themselves. And so we used a grid of analytic models based on Brian Metzger's prescriptions. So actually every small square in here represents an analytic model for that ejecta mass and velocity pair. And so this is all parameterized for a very low electron fraction, meaning a very neutron-rich ejecta that also creates a lot of heavy elements. And we only had one gamma ray burst for this really low electron fraction that was able to rule out a fraction of the parameter space. We also plotted on there estimates from both kilonova models and kilonova candidates and 17 GFO. So that's just the very red kilonova grid. But if we look at bluer kilonova models, then we find that our short GRB sample is better able to constrain the blue ejecta diversity more strongly. And then I should note our caveat that these constraints are highly model dependent. I think any kilonova theorist would tell you that there's a lot of work to be done there. And these can vary on the order of even up to 1/10 of a solar mass. And so just on this first point here, if we look towards the future and how can we start to probe more of that grid of parameter space where we're really understanding the R process better, I think we have a couple things to look forward to, a couple missions. So JWST cycle 1, Ido Berger has a program to follow up a short GRB kilonova there, just waiting for an event to trigger on. And then the Nancy Grace Roman telescope launched in 2026 will give us more photometric instruments to use to follow up these events. Okay, so back to this. Here again is the short and long GRB paradigm. Before I hop over to these kinds of events, I actually have one that pops up in the middle here. So this is the event that I was invited to talk about. This is the long duration GRB 211211A that was discovered a little over a year ago. And so this event was discovered by both Swift and Fermi. It had a really interesting gamma ray light curve. So if we just take it at face value, this is just two of the diagnostics on this plot that we usually use to separate short and long GRBs, the duration, and then the spectral hardness ratio, we see that this GRB falls squarely amongst the long gamma ray burst population. So taken at face value, it is a long GRB. However, if we look at the light curve in more detail, we notice that there's this spectrally hard complex that lasts about 12 seconds. So that still falls above our 2-second ratio, meaning it's still, even if you just take this part of the light curve along gamma ray burst. We also have this tail of softer extended emission. So this is something we do see in about 25% of short GRBs, but they're all accompanied by a very short spike. And so what was most interesting about this gamma ray burst light curve is that it resembles that of a past Swift GRB that was detected 17 years ago, 06/06/14. And so this event happened at a very low redshift. And what was so exciting about it is even though it's naively a long gamma ray burst light curve, there were very deep upper limits on a supernova. So no supernova was detected, and it didn't come from a typical massive star origin. So the next really exciting ingredient in this follow-up story is that we detected the afterglow to this event, and it was very close to a galaxy with a photometric redshift that was very low. This was later confirmed with spectroscopic follow-up at only 350 megaparsecs. So this is just a few days after the burst, we detected the afterglow in the optical. Swift and several other telescopes were on it right away. And you can see just the optical near-infrared SED here. It's relatively flat at early times. It gets a little bit redder, but it's relatively flat. So because it was so close to this nearby galaxy and we had this really interesting light curve, what my team did is we triggered follow-up with Gemini North in the NEARI instrument. And we discovered this bright infrared excess, especially compared to the optical, at only 4 days following the GRB. We had some other weather things that happened with it, so we switched to using MMT mirrors, but we were able to detect this near-infrared excess for 5 epochs. Later, we got Hubble Space Telescope imaging that showed nothing at the location of the infrared transient. This was further evidence that this was truly the host galaxy of this event and that there was no other more likely background source contaminating our observations. So this is a plot of the light curves after we've subtracted an afterglow model off using the X-ray observations and a radio upper limit. And so what we see is for that very first detection that we have, it's nearly the same K-band luminosity as 17 GFO. We also see that the K-band fades on a very similar timescale to 17 GFO. So what I should have mentioned right at the beginning is that these dashed lines are the light curve of 17 GFO if we shift it to 350 megaparsecs. So you can see it looks very similar in the way it fades. Okay. So I'll leave it on this pretty press image. So this allowed us to conclude, along with vetting several other hypotheses, that this was the second closest kilonova to date following 17 GFO, and it comes from a very surprising source, a 50-second duration gamma ray burst 2112 11A. And so this paper was recently published in Nature. We did some really wonderful press releases for it. They made beautiful images for us. And I think most excitingly, it opens up a whole lot of new questions. So what are the implications for O4? A lot of people are really interested in what the host galaxies of these neutron star mergers looks like. And having just another one in a local universe that's so different than 170817's host is really interesting. We also wonder, what are the rates of these events? What is the source of extended gamma rays? And then what can this tell us about the average ejecta mass per kilonova? So I'm just going to go through a couple of those, but feel free to ask me my thoughts later on any of the other questions. But so we did fit this with a 3-component kilonova model. These are very similar plots to what I was showing earlier with the ejecta mass and velocity, but now I'm throwing on a lot more of the short GRB kilonova candidate estimate, and our event is in purple here. And so this is showing us that we're starting to build up the sample, and we're starting to explore this parameter space. But for all intents and purposes, this event does fall in a very similar space to those of previous events, including 17 GFO. And then finally, what could have caused a 50-second duration gamma ray burst coming from something, coming from a neutron star merger? So the first thought is that it's not a neutron star merger. Maybe it's a neutron star and a black hole merging, and there's some late time fallback accretion from tidally disrupted material that causes this event to be, or this gamma ray burst to be sustained. However, we would expect there to be a redder kilonova if this was the case. And we do have a really large blue component when we model the kilonova and look at its light curve. Another possibility is that we just have a long-lived central remnant that powers the gamma ray burst for longer. But this is also tentatively favored due to the ability to explain a consistent extended emission timescale, where which we see in the X-rays. But I should say that all of these explanations are mostly developed to explain extended emission short GRBs. One thing that I don't think we necessarily expected to see is a 12-second pulse in the beginning. So there was another paper that came out in Nature in the same issue that suggested that this was a white dwarf neutron star merger. But I think that there's a lot of things you could throw at it to try to explain that extended emission. One hope that we certainly do have is that there would be a future coincident event like this, and gravitational waves and a gamma ray burst could decide it. Okay, so back to this plot here. Now I'll very briefly talk about core collapse supernovae as sites for our process element production. So why would you, if you already have a site for our process nucleosynthesis, why would you want to come up with another? And the first is that neutron star mergers, as I was talking to Flora about earlier, take a long time to merge, mega-year timescales, and it's difficult to explain observations of enhanced R process and low metallicity stars, as we've been seeing in the last few years. And so what we want is, or what would help us explain this better, is a formation channel that is more closely linked to star formation, with a shorter delay from star formation. And so this would happen if you take really massive stars and you have them creating some R process ejecta as well. And so this paper came out by Dan Siegel in 2019, where they did radiative transport models of these core collapse events, these collapsars that are rapidly rotating. And they find that if you have a very high fallback mass rate, you can actually have weak interactions in that disk ejecta that will neutronize the ejecta, pushing down that electron fraction and making it able to produce heavy elements. And indeed, if you have a really large disk, which you would expect to have in the case of a rapidly rotating star, the supernova might even contribute more than kilonovae do. However, not much has been able to be done on the observational side to search for this. So one way that I am really interested in doing this is doing searches using long gamma ray bursts as signposts. So as I said in the beginning, we have detected several gamma ray bursts supernova in the past. However, so this plot is showing time since the gamma ray burst, and I did some searching in the literature and trying to find some color magnitude measurements that were made in approximately similar epochs, and then compare them to models for what it would look like if there were a certain amount of R process in the ejecta over time. And we just don't really have the observations there. There's this dearth of observations that are really able to probe this question of if long GRBs or long GRB supernova can create R process. And so to explore this parameter space, I got an approved Gemini proposal to get observations of the optical NIR color evolution of a long GRB. And hopefully I hope to give you a talk that says we have distinguished GRB and R process in the supernova. Yeah. So these are my conclusions that rest frame optical sGRB kilonova span a factor of 100 in luminosity. And we have upper limits that constrain ejecta masses of 6 events to less than 500ths of a solar mass. We have the long GRB 211211A that was accompanied by a fast-fading NAR transient that strongly resembles the kilonova 17 GFO. And this demonstrates that long, complex gamma ray light curves can spawn from a neutron star merger event. And then finally, long GRBs that are accompanied by supernovae may be an alternate site to probe for our process production. And then before I conclude, none of this work happens in a vacuum, and I'm very grateful to a wide swath of collaborators, most especially my advisor, Wenfei, and our research group. Happy to take any questions.
Thank you so much. Let's start questions from audience here.
Fairly rudimentary question. If you have a GRB that's 1 second or 3 seconds, do you have any way of distinguishing those outside of just cutting the side of the line around?
Yeah, so that's a good point. There is definitely overlap in the populations, as you can kind of see here from this Fermi collection. However, I think you can even kind of see it visually here, that to have a event with such a long light curve, there must be something unique about it. It's not just, statistically possible. Yeah.
The thing near the borders, like a 1 second or 3 second.
Yeah, so there has been kind of recently, there was also a GRB with a duration of 1 second that had a supernova counterpart to it. So there is certainly some overlap in the population. And even if I go back to this plot, you can see that we do expect there to be some interlopers. However, what was so interesting about this event is that it was 50 seconds. So way past that cutoff of 2.
All right. Would this event have been detected with the advanced LIGO if it was operating?
Yeah, so we had some of our LIGO friends do those calculations for us, and they said, so of course you have to estimate what the binary neutron star masses would be in this case, and I think for 03 it would have been detectable significantly as a neutron star black hole event. In 04 it would both a 1.4 solar mass neutron star binary and a neutron star black hole would be detectable. Those are the predictions. There was another paper that said that they reran their own calculations and they found it would only be detectable at 04. I'm not an expert on this analysis at all, but I think it's kind of on the edge, and certainly a low latency search would have been possible.
So presumably people have done population calculations with the kilonova rate to see whether you get enough R process material to match solar abundances, for example. And do they, or is there a gap and you need an extra source?
Yeah, that's a great question. So they are certainly highly uncertain. So actually, I think if you take 170817's yield, or the yield that most people inferred straight from the observation, you do actually overproduce solar abundance at this point. But I think that there's still a long way to go in understanding how you get from our process heating and thermalization efficiencies and opacities back to the R process that you infer, because this field is so new, right? We only kind of started in 170817 developing these kilonova models. And I think that the evidence that you need a fast merging channel is very strong, because having a neutron star merger, there are these like significant populations of low metallicity stars with high amounts of R process in them. So it's not just a single dwarf galaxy. There's a few populations.
Questions? No? Okay, so let's thank both our speakers again. Thank you so much. See you next week.
I don't know what to do.
Thank you.
Thanks. I got nervous. I don't know why.
Okay, the computer is Xiurui, right?
Yes.
Hello.
Oh, sure.
You're Amy? Yes. No one would ever know that.
I should introduce
You should, in the nature of everybody else, but not you. So,
next time. Good
So-
point.
and the whole point of you doing this is to be known, I think, right? And please use the microphone because you.
Those are part of the cheer.
This in this today, which I did.
Yeah, it's very nice, very interesting.